Our next topic is roll center and roll dynamics of a vehicle. Similar to a pitch rotation that was discussed in the previous video for the case of acceleration and braking, the vehicle performs a roll rotation during cornering maneuvers due to inertial forces and the vertical elasticity of the suspensions. This roll rotation is always in the direction of the outside of the turn. So for instance, during a left turn, a positive roll angle is achieved. The corresponding rotation axis, shown from this perspective as the yellow dot, is called the vehicle roll axis. Clearly, it is better to illustrate the vehicle roll axis from a sidewards perspective onto the vehicle. So in this picture, it is shown as the yellow dashed line. The precise geometry of the vehicle roll axis is defined by 2 points, one that corresponds to the front suspension of the vehicle and it's called the front roll center, and one that corresponds to the rear suspension of the vehicle that's called the rear roll center. Before we continue, let's look at some remarks about the front and rear roll center. First, similar to the virtual pivot points for the pitch rotation, the location of the front and rear roll center is determined by the kinematics of the front and rear suspension, respectively. Later in this video, we'll look at how to actually determine the location of the roll center of a suspension from its geometry. For now, we just take it for granted that such a roll center exists for every suspension and that its position is given to us. Moreover, we should keep in mind that a fixed vehicle roll axis is just a simplifying assumption, albeit it's a very good approximation of reality. In reality, however, the vehicle roll axis slightly changes with the vehicle's roll angle and pitch angle. Nonetheless, for simplicity of the analysis, we will hence assume that there exists a fixed vehicle roll axis. Based on this, in a thought experiment, we may rotate the chassis around the vehicle roll axis. For this, we will need a forcing moment, which is counteracted by another moment that's caused by the suspensions. The corresponding rotational stiffness to this rotating motion, which carries the unit Newton meters per radian of pitch angle, is called the front and rear roll stiffness for the front and rear suspension, respectively. We will now proceed to take a closer look at this rotating motion around the vehicle roll axis. Let's consider the rear suspension of the vehicle. The front suspension is analogous. To this end, we'll look at the vehicle from a backwards perspective with the rear roll center shown in yellow here and the center of gravity shown in purple. As we did for the pitch dynamics in the previous video, also for the roll dynamics, we only consider the difference of forces compared with the static equilibrium of the car. In other words, as long as the vehicle does not perform any lateral motion, we will not show any forces acting on the vehicle. This is despite of the fact that, of course, the weight of the vehicle is attacking in its center of gravity and it's cancelled out by the vertical tire forces. However, since these forces are in static equilibrium, we may ignore them and only consider the difference of forces compared with the new quasi-static equilibrium that the vehicle finds itself in during a stationary cornering maneuver. So suppose the vehicle is now in a stationary cornering maneuver to the right. Then there will be corresponding lateral tire forces acting on the two rear tires. These two tire forces both have a moment with respect to the center of gravity of the vehicle. However, the vehicle is in a quasi-static state while cornering. Hence, this moment has to be compensated by a moment of equal size and opposite sign that's caused by a change in the vertical tire forces of both tires. So, as drawn in the diagram, the changes in the vertical tire forces, delta FCRR and delta FCRL, compensate for the moment of the lateral tire forces FYRR and FYRL. In order to see what forces are responsible for the body roll, let's draw the free body diagrams of the suspension and the chassis. What we already know are the lateral and vertical tire forces acting on the rear right tire and the rear left tire. What we want to construct now is the fraction of the vertical tire forces that goes through the stiff parts of the suspension and the other fraction that goes through the springs of the suspension. So equivalently to the anti-dive and anti-squat of the pitch rotation. The fraction of the vertical force that goes through the stiff part of the suspension and hence causes no body roll is constructed by drawing a line from the rear roll center to the midpoint of the rear wheel, and then the yellow fraction of the vertical force will be such that the combination with the lateral tire force points exactly towards the roll center, and hence it has no moment with respect to the roll center. The same, of course, holds for the right tire, and the combinations of the vertical forces and the lateral forces, shown in orange here, are transmitted via the rear roll center to the vehicle chassis, and hence they act as a axio-reaxio pair between the chassis and the suspension. Now that we've seen how the lateral tire forces and the yellow parts of the vertical tire forces get transmitted to the vehicle chassis, what about the remaining parts of the vertical tire forces? These parts of the vertical tire forces, shown in green here, are passed to the vehicle chassis via the springs of the suspension. They appear again as axio-reaxio pairs between the tire and the chassis. Clearly, this will lead to a compression or extension of the corresponding suspension. To summarize, we have that the total vertical tire force on each tire is equal to the yellow plus the green component, where the yellow component is called the jacking force. Moreover, from the geometry it follows that the jacking force is given by the fraction of the height of the rear roll center divided by the height of the center of gravity, and correspondingly the green force makes up for the rest of the vertical tire force. In order to interpret these results, let's consider some extreme cases. In the first one, HR equals to H, which means that the rear roll center and the center of gravity coincide. In this case, all of the vertical tire force will be directed through the stiff parts of the suspension, and hence there will be no force that compresses the springs of the suspension, and therefore the roll angle of the chassis remains zero during all turning maneuvers of the vehicle. This fact can also be explained more intuitively. By definition, the roll center represents the point where the vehicle can be pushed sidewards without any effect on the roll angle of the vehicle. Now clearly, if the vehicle is in a turn, the sidewards force is an inertial force that attacks at its center of gravity. So if the center of gravity and the roll center are identical, that means there will be no body roll during turns. In the next case, HR equals to 0, which means that the roll center is located on the road surface. In this case, all of the vertical tire force passes through the springs of the suspension and hence causes the chassis to roll. Now that we understand the situation for the rear suspension, remember that the front suspension is analogous, we turn our attention to the coupling between the two. The coupling is, of course, due to the common roll dynamics of the vehicle chassis and the roll stiffness. Now we consider the full vehicle with the front and rear suspension, and hence with the front roll center and the rear roll center and the vehicle roll axis that passes through both roll centers. Suppose there is some unspecified moment that we call m phi acting around the vehicle roll axis. For this situation, in the stationary case, meaning for phi double dot equal to 0 and phi dot equal to 0, the quasi-static roll angle delta phi of the chassis, meaning the difference in the roll angle compared to the situation without the moment m phi, is given by m phi equals to the roll stiffness k phi times delta phi, or solving for delta phi equals to m phi divided by k phi. Next, let's look at how we can obtain an expression for the roll stiffness k phi by looking at the front axle and the rear axle in combination. Note that the two are coupled by the fact that the roll angle delta phi is the same for the front and the rear axle. Let's start by looking at the front axle. In the stationary case, due to the moment m phi, the left suspension will be compressed and the right suspension will be extended. Since the vehicle roll axis passes through the middle of the vehicle, the distance from the pivot point of the front axle to the left and to the right is the same, and it's equal to half of the track width b. By means of a small angle approximation, the compression distance of the spring of the left suspension and the extension distance of the spring of the right suspension both equal to b divided by 2 times the angle delta phi. Hooke's law for the two springs implies that the compression force acting on the left suspension and the extension force acting on the right suspension are identical, even though they act in opposite directions, of course, and the magnitude is given by the stiffness of the front suspensions, kf, times the compression or extension distance, b divided by 2 times delta phi. And the same thing holds for the rear axle, of course, only that now we're talking about the rear spring forces on the left and on the right, and we have the stiffness of the rear suspensions, kr. Now, setting up a balance of moments around the vehicle roll axis yields that the moment m phi must be equal to the moment produced by the front axle plus the moment produced by the rear axle. By substituting the expressions for the spring forces that we have just derived up here, we obtain an explicit expression for our roll stiffness k phi. So the roll stiffness k phi equals to the sum of the front suspension stiffness kf and the rear suspension stiffness kr times the track squared divided by 2. Next, let's derive an expression for the particular roll moment m phi that's generated by a stationary cornering maneuver. To this end, we consider a balance of forces that act on the vehicle in the horizontal direction. These horizontal forces are summarized in this partial free body diagram. By the center of gravity principle, we can state that the mass times the lateral acceleration of the vehicle is equal to the sum of all forces acting in the lateral direction on the vehicle So the sum of all 4 lateral tire forces on the front left, the front right, the rear left and the rear right tires. Note that we may add m times a lat as an inertial force acting on the center of gravity in order to obtain a quasi-static free body diagram. In order to derive the roll moment m phi that is caused by the inertial force m times a lat, we look at the vehicle from a sidewards perspective. The yellow axis that passes through the front roll center and the rear roll center is the vehicle roll axis, and the inertial force m times a lat acts on the center of gravity from the other side of the vehicle. The lever arm of the inertial force with respect to the vehicle roll axis is approximately equal to the difference between the height of the center of gravity and the height of the roll axis at the point of the center of gravity. By using some basic geometry, hc can be calculated in terms of the height of the rear roll center and the height of the front roll center, as well as the lengths LF and LR. In fact, hc equals to hr weighted by LF plus hf weighted by LR divided by L, the wheelbase of the vehicle. And substituting this result into the formula that we obtained up here yields this expression for the roll moment. Together with the formulas for the roll angle delta phi and the roll stiffness k phi from the previous page, we obtain this formula for the corresponding roll angle delta phi during a stationary curve. Hence, again with the formulas of the previous page, the elastic vertical tire forces of the suspension read as shown in this box here. Remember that the left and the right forces at the front and at the rear do point in opposite directions. For now, the interesting part is this first fraction in both expressions, which basically shows that the difference in the tire force between the left and the rear tire is proportional to the corresponding stiffness of the front and the rear suspension. Or, explained more intuitively, the vehicle is rotated by a common roll angle delta phi, and now the stiffer the front suspension is, the more will this roll angle lead to a difference in the front vertical tire forces, and the stiffer the rear suspension is, the more will this roll angle lead to a difference in the rear vertical tire forces. Let's summarize these findings in a few remarks before we continue. First, the total roll stiffness k phi is given by the sum of the front and the rear roll stiffness, k phi f and k phi r, which in turn are given by an expression involving the front suspension stiffness kf and the rear suspension stiffness kr, respectively. Second, the difference in the vertical tire forces, where difference means with respect to the static equilibrium, consists of the sum of the jacking forces, which were denoted Fj for each tire, and which pass through the rigid parts of the suspension, and the elastic forces, which were denoted Fs for each tire, and which pass through the springs of the suspensions. Third, during a stationary cornering maneuver, all of the vertical tire forces on the left-hand side have the opposite direction and the same magnitude as the corresponding one on the right-hand side. And finally, the magnitude of the front elastic force pair and the rear elastic force pair is determined by the ratio between the roll stiffnesses of the front suspension and that of the rear suspension, meaning the higher the roll stiffness of the front suspension, the higher is the magnitude of the front elastic force pair, and the higher the roll stiffness of the rear suspension, the higher is the magnitude of the rear elastic force pair. And that brings us right to our next question. Why does the difference between the left and the right tire forces matter? And the reason is, of course, that the lateral tire force of a tire depends on its vertical tire force. For the dynamic bicycle model, remember that the idea was that we did not distinguish between the left and the right tires. Instead, the left and the right tires at the front and those at the rear were lumped together, and so were the corresponding lateral tire forces. So the tire force at the front was given as the sum of the tire forces of the front left and the front right tire, and the same thing for the rear tire. As we have seen in the video on lateral tire models, the lateral tire forces do not grow proportionally with the vertical tire loads. In fact, a lateral tire force grows subproportionally with the vertical tire force, as shown in the diagram on the right-hand side. Note that the yellow curve represents the relationship between the vertical tire force and the corresponding lateral tire force of a specific tire for a given slip angle alpha. Hence, if both tires of the same axle, meaning the left and the right tire, have the same vertical load Fc star, then the total lateral force generated by this axle is given by 2 times the corresponding lateral tire force Fy star. We now compare this with the lateral force that is generated by a left and a right tire that deviate from the average vertical load Fz star by plus minus delta Fz. By the fact that the relationship between the vertical and the lateral tire force is concave, we see that the total lateral tire force generated by Fc star plus minus delta Fc is actually lower than the one generated with the identical vertical loads. So we conclude that if we increase the roll stiffness of the front or rear axle, this results in a decrease of the lateral tire stiffness of the lumped front or rear wheel of the bicycle model during a cornering maneuver of the vehicle. This is a very important insight into vehicle dynamics, and we add the following concluding remarks. First, a higher roll stiffness of the front axle decreases the total tire stiffness of the front axle, and hence it increases the vehicle's understeer, especially at high speeds. Obviously, the converse is also true, meaning that increasing the roll stiffness of the rear axle increases the vehicle's oversteer. However, oversteer of a vehicle should be avoided, especially at high speeds, because it leads to instability of the vehicle above a certain critical speed, as discussed in the corresponding video. Therefore, designers usually pick the front roll stiffness large enough in order to avoid this oversteer behavior, even in dynamic cornering maneuvers. To this end, the roll stiffness of the front and rear axle can be modified, or more precisely, it can be increased by the addition of an anti-roll bar. An anti-roll bar is an elastic bar that is fixed to the vehicle chassis, and it alters the stiffness of the suspension, but only with respect to the rolling mode of the suspension, meaning only with respect to one tire going up and the other one going down at the same time, but it does not change the stiffness with respect to both tires simultaneously going up or down. Moreover, in practice, due to the undesirable jacking forces that were introduced earlier in this video, the roll center of any suspension is usually kept closely above the road surface. And finally, in practice, to avoid excessive roll rotation of the vehicle chassis, the center of gravity should be kept as closely as possible to the vehicle roll axis. As the last topic in this video, let's look at the geometry of the roll center. In fact, this topic is very similar to the anti-dive and anti-squat suspension geometry that we have considered in the previous video. So, analogously, there exists a virtual pivot point of the suspension with respect to the roll direction of the vehicle. In the following, we show how the virtual pivot points and the roll center are constructed by using example suspensions for which all of these points are kinematically well defined. Again, we start with the double wishbone suspension, and in the first step, we aim to construct the virtual pivot point of the suspension around the vehicle, but now in the roll direction. In order to construct the virtual pivot point of the left wheel, which is the point around which the left wheel pivots when it moves up and down, the two lines which correspond to the geometric orientation of the upper and lower wishbone have to be extended and intersected. By looking at the suspension in more detail, these lines can be seen as a connection between the front joint and the middle of the rear rotation axis for the upper and the lower wishbone. If the same thing is done for the right suspension, it yields another virtual pivot point for the right wheel. Now the question is, where is the roll center of this suspension? What we know is that if the chassis of the vehicle was fixed in space, then the left wheel would pivot around the left pivot point and the right wheel would pivot around the right pivot point. If the wheels were fixed instead, then it would be the chassis that pivots around these 2 points. Or specifically, if the left wheel was fixed, then the chassis would pivot around the left pivot point, and if the right wheel was fixed, then the chassis would pivot around the right pivot point. Now, obviously, the chassis cannot pivot around both virtual pivot points, but also the 2 wheels are not really fixed. Instead, what is fixed is only the contact patch between the corresponding tire and the road. In our assumptions, this contact patch is represented by the midpoint of the contact patch for each of the tires. So the assumption is that the wheels are fixed at these 2 points, but otherwise the wheels can tilt to the outside or the inside, which is called the camber direction. Based on these assumptions, we now have that the left wheel pivots around this point and the chassis again pivots around the left wheel. Therefore, the velocity vector of the left virtual pivot point must be perpendicular to the connection between the midpoint of the rear tire and the virtual pivot point. Note that this is not true for any other point of the vehicle chassis, because any other point has an additional velocity component due to the pivoting around the virtual pivot point. Hence, we deduce that the roll center must lie somewhere on this white dashed line, because the roll center can only be the center of rotation if every point of the chassis has a velocity vector that's perpendicular with its connection with the roll center. Now, the very same argument, of course, applies to the right tire of the vehicle, from which we conclude that the roll center must lie on this white dashed line. Since the roll center now has to lie on both white dashed lines, it has to be equal to their intersection point. A similar construction can be made for the McPherson strut suspension. In fact, the lower control arm of the suspension is analogous to the lower wishbone of the double wishbone suspension. So one line for the location of the virtual pivot point is given by the geometric orientation of the lower control arm. And the second line is perpendicular to the strut and passes through its upper end. The same thing is of course performed for the right suspension, which gives us the virtual pivot point of the right wheel. With these two virtual pivot points of the left and right wheel, we can now apply the very same argument as for the double wishbone suspension. So we define the midpoints of the tire road contact patch and connect them with the two virtual pivot points. Since the roll center must lie on both of these white dashed lines, it is located right at their intersection. Note that the roll center is also defined for other types of suspensions. Depending on its construction type, it may be more or less kinematically well defined. Its construction is particularly intuitive for the double wishbone suspension and the McPherson strut suspension. That's why we chose it as examples here. If you properly understood how to construct the roll center for these two suspensions, it will be possible to construct it also for all other types of suspensions.